Hey then, we have a clap. You all know what that means. Hey guys, what's going on? Yes. After last week, spending most of the week on the road, driving across the good old US of A, I must say, at least west of the Mississippi, there are a lot of gas stations that have a lot of locally made tasty snacks. I appreciate that. But yeah, we're back in the Commonwealth now, and as we'll let everybody come on in from the different parts of the internet. I know we took a week off. We took a week off. Yeah, you gotta drive like 2,500 miles after you replace your engine twice in one year. That poor car had like literally three different engines in it over the course of about 4 months. I digress. It's all right. We're back. We are operational again. By operational, I mean I literally just put up this 3x4 whiteboard. Yes, I tried to use a level and everything. I'm not sure how perfectly level it is, but it should be level enough for what we're doing. Okay, I should have really wore the level up shirt. I should order more while I'm back here on this coast side. But all right. So rather than belaboring the point, we're gonna jump right in because the title of today's yes, I have it set up this way mostly because this room is an absolute mess. And I figure I'm like, well, this is the current table we have, and then I can just kind of right up here and it'll be right here the whole time. Rather than being like, can I barely see that thing? What is going on? It seems to make more sense to me. All right. So we're going to be talking about a really large number hypothesis. Why am I bringing this up? Well, good old Professor Paul Dirac, he had hypothesized something long ago about the really large stuff within the universe as relationship to different force type things. Okay. Why do I say that? Because it's a link in the doobly doo. And if we do the whole, we'll go to our friend Wikipedia. Let's share with a class. The terminology that one would look for would be large number hypothesis or Dirac's large number hypothesis. Hey, upcycle. We're just we're getting a little bit more direct because I know a lot of times you'll put something up and there'll be stuff on the board, and I'm like, all right, that's probably a brilliant thing. I see it on different like from the Institute for Advanced Study, where Professor Ed Witten is a member, along with even the ICTS. I'll see all this stuff and things on the board, and a lot of times I don't know what any of it means. Occasionally I'll pick through, and there'll be things that I can recognize and stuff. So I'm like, all right, rather than me putting a board, that stuff it might make sense to me. Maybe it's brilliant. It's probably just numerology, because remember, numerology is numerology until you explain more with less. Then it becomes adopted. Okay. So Dirac's large number hypothesis. This is from our friends at Wikipedia. All right. The large number hypothesis, LNH, is an observation made by Paul Dirac in 1937 relating ratios of size scales in the universe to that of force scales. The ratios constitute very large, dimensionless numbers, some 40 orders of magnitude in the present cosmological epoch. According to Dirac's hypothesis, the apparent similarity of these ratios might not be mere coincidence, but instead could imply a cosmology with these unusual features. For example, the first bullet point is the strength of gravity, as represented by the gravitational constant, is inversely proportional to the age of the universe. I believe that's was it G adjoins, was it 1/T? So T would be they're about 13.8 billion-ish years. The mass of the universe is proportional to the square of the universe's age. In this case, big M, our total observable stuff in our observable universe, adjoins T square. All right, physical constants are not actually constant. Their values depend on the age of the universe. Okay. So and they go through and some of the interesting things here. If you take like the radius of the electron, about 10 to the minus 16 meters, and You compare it with the radius of the observable universe, you get like 4.1 times 10 to the 42, that ginormous number there as a relationship. Okay. Now you get that, and then you take, what is it? Okay, so you take, it's basically the fine structure constant there, except they removed h bar, and then they have the mass of electrons squared, and they have big G instead of h bar and C in there, respectively. Okay, so yeah, that appears to be basically the same number, 10 to the 42. Okay, and this was Arthur Eddington's conjecture for the number of charged particles. Is that true? I'm pretty sure most folks don't think so. Um, again, could be totally wrong, could be totally right. But it's an interesting thing. I know, what is it? Dr. Unziker has been talking about this for a while, and everything is going to be at Demystify Sci's cosmological conference over there in Portugal. I think, when is it? Is it March? Is it June? Is it sometimes there? I don't know. Shout out to Anastasia and Shiloh from Demystify Sci. Uh, okay. So what are we talking about? Okay, so we don't need that. We need to go back to the board. Okay. So as I blatantly wrote on the board, there's a conjecture. All right. We're gonna conjecture that the mass of the universe, or M. Let me learn how to use a marker again. Oh, this is a good marker. M U. We're gonna use lowercase u there. Because it's universe, aka our Roman persistence. I don't big U something else. Okay. So mass of universe over the mass Planck, aka the Planck mass. All right. Put our protective brackets over there. Why? It makes me feel better. Better to have them and not need them than need them and not have them. All right. I'm going to set that equal to. Yes. And we're going to do friend meters. Okay. So I can't just use little m because I'm already using it for mass. You do meters over. How about this? Well, we're doing the maximum of mass, which is very interesting. The maximum particle style thing, because I don't think you can get smaller than a Planck mass black hole. Could be wrong. All right. We're taking a maximum expression of mass. No, excuse me. We're taking the sum total of mass, dividing it by a maximal expression of mass, and then taking our unit of length, and we're dividing it by the minimum of length, the Planck length. We're going to put our brackets on to feel better about ourselves, and we're going to square it. And that's I am not mirroring this. This is not. Oh, wow. This is weird. Everything is backwards. Hold on. Hold on. I can't have this. What happened? It doesn't normally do this. What have I done? Hold on. Settings, camera, mirror my camera. Oh, there we go. Okay. Wow. That kind of hurt my head. I'm like, what did I do? What have I done? Okay. There we go. The moment you gaze into the mirror and the mirror gazes back, and you're like, WTF, mate. All right. Okay, much better. All right. So now that we are in the proper symmetrical frame, I understand I don't have a beard, but it's okay. We're gonna make it. Uh, okay, so what the heck is this claim here? All right. The claim is this. All right. This is why I call it a really large number hypothesis. All right. We're going to claim that the mass of universe divided by the Planck mass is equivalent to meters divided by the Planck length squared. Okay. I mean, that's a crazy thing to say, and you should totally believe it's crazy because it's coming from a crazy person on the internet. Now, remember, numerology is numerology until it explains more with less, I claim. Okay. The claim part is important because otherwise now you're making a statement and it's like, okay, maybe you have divine inspiration. I don't know. Maybe that's it's more of a philosophical question. So let's actually get into what we're talking about. Okay. How can I justify the words coming out of my mouth? Well, let's share with the class, shall we? All right, we'll go to our friend over here, Wolfram Alpha, and we're gonna do a claim. Okay. So originally, oh, we should get to one other thing. Hold on. I need to lay out one other thing before we actually get to justifying this. Okay. So I'm gonna make a second claim here. The second claim is that I'm gonna do the radius of the universe, so we'll do big R sub U. Okay. RU is equal to. So it's going to be equal to, and it should be this. And again, meters squared over blank length. Okay. That is the second claim. To be fair, this helps reinforce this claim under. Okay. Why am I using these? The Planck bases are boundaries we happen to have found within physics as we know it. These are limits for different things. Coincidentally, you can use just 5 of them to model reality, time, space, or length, because you have the different derivatives to get an area, volume, and stuff like that. All right. You get charge, you get mass, and you get temperature. And when those Planckian units and dimensions of reality combine, well, you get where we live in the proper configuration. Cool? Okay. So the reason I'm showing you this, because this will give us an explicit number. Okay, what's this explicit number we're going to get? All right, so let's share our window over here. Don't mind any of that jib jab there. All right. So this number here, what do we have? I like my little protective brackets. Meters squared over blank length. This is literally what you do. You type in the magical words and it does the computation for you. Yeah, I mean, the sheer efficiency you can do it, and you can just go into a notebook, and so you have like an Excel spreadsheet. You go through, you do this, you do that. It can make researching a lot faster. Okay, so what do we get when we do that? We get like 6 times 10 to the 34 meters. That's ginormous. So what's it relative to? Coincidentally, Wolfram Alpha also tells us that. Okay. So we're pushing upwards of 8 times the diameter of the observable universe. Excuse me, 8 magnitude. So it's basically, what is it? Oh, a million is 6 zeros. So if you go to that thing, yeah, it's about 100 million times larger than the radius of the observable universe. Maybe it would look like there isn't much curvature. I'm just saying. All right. So it gives us a number. How long would it take to travel that way? Okay, that would take a good deal of years. All right. I'm doing my own research that I should have done in other places. Okay. See, it's a learning environment. It's a learning environment. People say things in here, and it's like, oh my God. Thank you guys for joining now and temporally in the future. Because you'll see a comment, and it's like sometimes just that one comment, it's like, oh, duh. Okay. So this gives us a number. So we're going to claim that's the radius. This is that RU of the observable universe. That RU is basically this big number here, excuse me, or technically this really large number. Okay. So we have that really large number. Okay. So here's what we're gonna do. We're gonna take that really large number. Okay, I'm gonna make a little tab there. Why? Okay, because this whole mass of the observable universe, how can I justify this? Because I can just say this and that'll give you a number, and maybe it's a convenient number, but there are other ways to figure this out. Okay. So Dr. Salvatore Pius and Rick DeWitt have both, I've seen use this technique here, where we just go right back over here, and we assume that, let's say that something was constant. Hypothetically, let's say the Planck force, or as Dr. Salvatore Pius may say, the super force. We take the super force, okay, the Planck force, what do? We literally just type Planck force. Okay. It gives us the information. C4 for big G. Oh, is that like a C4 convention or something? I don't know. Okay. It's basically 10 to the 44 newtons of force because it's in the dimensions of mass, distance. So mass times distance, mass, length, and it's an acceleration because it's time squared. So it's mass, distance, acceleration, force. Cool. All right. So let's say hypothetically you did, I don't know, you're trying to calculate. You know what? I actually need to go back to my last video because I still forget how I did this. It was one of those things. Hold on. Wait, how do we do it the last time? Oh, wait. I have the links in the doobly-doo to this one right here. Here. Helps if you have the answer. All right. Planck force to estimate. I'll bring it here. There we go. Okay. All right. So the reason why we needed this RU, this radius of universe. All right. So we got our meter squared divided by the Planck length there. All right, cool. So this is what we did here. We have our meter squared divided by the Planck length. So the way this is set up is the claim that I have heard said that if you set it equal our realm of persistence, our universe, so to speak, small u I'm going to use, the Planck force equal to the mass energy of universe, and if you happen to know its radius, you should be able to solve for the mass. So the claim is that the total mass energy of universe should be divided by the radius of universe should equal the Planck force. Okay. When you do this computation, you get out this ginormous number here. It's really big. Oh, it also appears to be quadratic, so because it's at 4 times. Okay. Let's go to that. So we were solving for x here. So basically we have the Planck force set equal to, and we're going to solve for x. If you happen to have the estimated mass, you could solve for this. That's the claim. Okay. So we're solving for x kilograms because we're taking the mass. We're taking its mass energy equivalent there, c squared. Gives us this ginormous number. So since we're solving for kilograms, we toss our dimension back in. Okay. So what is this? All right. This is about okay, so it's going to be 3 orders of magnitude less in kilograms. All right. So we have about 61 kilo because we express it in that way because that's the way we've done it for a long time. Okay. You get about 8 times 10 to the 61 kilograms, or 8.33. It was actually 1.5, so that rounds up there. All right, so that's about 8 orders of magnitude, the mass of ordinary matter within our observable universe. Pretty cool. All right, so we're going to continue. So we got that number there. We have the Planck force. But names, why? Why are you showing us this? Why are you showing us this? Okay. Believe in computational reducibility. Why? Because otherwise, I don't think we would be doing any of these things here. People wouldn't be able to remote view or how the algorithm pass this off to you as something you think you might enjoy. I mean, who knows? I'm not just another crazy person rambling on the internet. It's okay. You can ramble into the digital ether, but not the ether, because that's not a thing. Why? Because it's it's a 5-letter word. We can say space time. We can say superfluid. Don't you dare get going on the ether, but no ether. Okay. So what we're going to do is that thingy behind us is we're going to do the same thing. We're going to solve for x. The mass of the universe. We're going to just put x kg for kilograms. We're going to divide that by the Planck mass. And we're going to set it equal because we got to solve for x. We're going to set it equal to something. All right. So we're going to make our claim. We're going to do meters squared over. Oh, wait. That's actually, no, this one. It's meters over Planck length. And then we square that whole dang thing because we need it to be dimensionless. It's giving us an answer here. Apparently, that seems to be. Oh, wait a second. The number right there, 3.8 times 0.28. Wait a second. I remember that number from somewhere. I think just. I think it's just this. Isn't it like 1 over the Planck length squared or something? Oh, lucky Lou. It appears to be the same number, slightly different dimensions because we just have a 1 over it, but it's the old noggin a jogging. Okay, so what's the number? We're trying to solve for mass here. What do we get? It seems to be another really large, ginormous number. Let's open it up over here. We're solving for kilograms. Note the tail ends do differ. They're using some slightly different factors there. So, but it's kilograms. Wait a second. This looks kind of familiar to something we got before. It's grams. So we go down 3 orders of power. Make sure we have the kilo in front of it because we need the kilograms. Wait a second. 8.33, approximately 2 times 10 to the 61. Wait a second. This seemed familiar from something. 8.33. 8.33. I mean, my friends, this kind of looks like the same number here for our estimated mass of universe. Yes, small u universe. Why? Well, if we're going to claim that there's a radius, and the claim of the length of that radius is pretty ginormous, about 10 to the 34 meters. So it's a little under 100 million times the observable radius of our observable universe. So, I mean, magnitudes seem to be about 10 to the 8 for each of those. But okay. Okay. Yes. We had some math there. Okay. What is the meaning of the math? What does it mean? What is the purpose? Okay. So it gets more interesting because if we go from that, we can then do this. Because if we take mass of a universe, let's do this. What are some other Planckian things that we may or may not know about? Well, let's check now, shall we? Let's go to our friend over here, back to the window, share with the class. Okay. Well, let's take this ginormous number there. Okay. How about something like, I don't know, the Planck density? Infinity. I can spell sometimes. All right. We got the Planck mass density. All right. What is that? It's C5 over big V squared times H bar. Okay, whatever that means. What does that come out to be? Well, that comes out to be 5 times 10 to the 96 kilograms per meters cubed, aka mass divided by length cubed in Planck units. Okay. All right. That is a ginormous number. Okay. So what happens if we take a really large number and we divide it by the Planck density? Does anything interesting happen? Wait a second. 1.616. That number looks very familiar. Let's take this number. Does this number mean anything to us? Now, here's what we're going to do. We're just going to search for meters, not meters cubed. Oh, wait a second. 1.616 times 10 to the minus 35. Oh, that appears to be the Planck length, my friends. The Planck length? No, it was not the Planck length. It was the Planck length times 1 meter squared. If we take our conjectured mass of universe, to be fair, this actually should be 5. Let's see if uh, 5 gives you the same number. But all right, so we take our conjectured mass of universe, whether we take it by calculating it via the Planck force, or we set it equal to the little thingy that we wrote on the board. So basically, well, the Planck mass, we know to at least 5 significant digits. Meters is our base unit of 1 for length. We get the Planck length to like 5 significant digits. You can just kind of algebra this stuff together and solve for x. And when we get our x, well, we get this number, that ginormous number, which coincidentally, if we take our ginormous number there and we divide it by the ginormous number that is the Planck density, we get 1 Planck length times 1 meter squared for our volume. You're to take all the mass of claimed in the universe and you were to scrunch it together. We'd be at, well, if we take, actually, we can just take this number. What would the radius be? Well, that's in a cubic form. So let's take the cubed root of it. So we raise it to 1/3. Do your magic, Wolfram Alpha. About 2.5 picometers, or 2.5 times 10 to the negative 12 meters. That's pretty small. Oh, looky. It's about the electron Compton wavelength. Cool. Now listen. I know there are a lot of folks out there that say, how did things begin? It started in a very hot, dense state. Why? Because that's the beginning to the Big Bang Theory. Well, depending on the Big Bang Theory, that's either the beginning of the song, or usually it begins with quantum fluctuations. We wave our hands, so we're basically halfway to casting a spell. We just need to speak the right magic words, so to speak. I don't know. I'm just saying, people want to start with a primordial atom. Cool. I mean, I'll bet 1 Planck length times 1 square meter. That sounds like a pretty primordial atom, so to speak. It's probably really dense right there, like maybe at the Planck density or so. It's a very interesting calculation, and it gets more interesting. Okay. Because remember our whole Planck force thing. What did we do? We multiplied it by c squared. Okay. What happens if we take that ginormous number and we multiply it by c squared? Let's see. So let's make another one over here. I'll take that. All right. And then we magically type c caret 2. C squared. It's magic. So it'll give us estimated mass energy, or the mass energy equivalent to the total sum mass of universe, I claim. When we get this number over here, we get 7.488 times 10 to the 78 joules. Okay. We put that in there. Okay. Don't worry, my friends. Well, we'll go back to some of the fun stuff. All right. So hypothetically, let's divide by another number. Let's say how about the all caps? All caps were really mad. Planck pressure under pressure. Okay, that's the definition in C7. The speed of light raised to the seventh power divided by the Newtonian gravitational constant square divided by h bar. Okay. 4.6 times 10 to the 130 pascals. Not Pedro Pascals, but Pascals. May or may not be a relation. Okay. So what happens if we take this magical term and we divide it into this magical expression that we had there? What do we get? WTF, mate? This looks familiar. Wait a second. 1.616 times 10 to the 35 meters cubed? The Planck length times 1 meter squared again. Why? Why does it line up in such a pretty way? I don't know. It's the old noggin a jogging. And again, I'm sure this is just some numerology. This has nothing to do with actual reality. Just a really large number hypothesis. Okay. Okay. So let's do this. We will add one more thingy to the bot. Okay. So we're going to do. How should we do this? Oh, let's just do it like this. Okay. So we're going to take mass energy. So we'll take the claimed mass energy of the universe again, lowercase u. So we're going to do m u. We're going to do our c squared because we can. Okay. And we got that really big number, like 10 to the 78 joules. All right. We're going to divide it by a friend. That friend's going to be the blank. Oh my God, I left the monastery for less than a week. I can't even spell blank. Well, I got an eraser for this, so it's still in the box. All right. The plank. There's one for you. Spring constant. All right. What the heck's a spring constant? Well, it's that thing that like first year physics students learn to do. It's what do we do? All right. We have an idealized situation. We take a spring, we attach it to the wall, we attach a block to it. We ignore friction because that makes it too difficult, and we're trying to communicate the point of a spring. Whereas you take that little thing that's on the let me ignore it. Okay. So the claim is you got your wall, got a spring on it. We attach it to a block because that's what we do. All right, we got our block on the spring. All right. So the thing is, if you go like this, if you go push it in, it will push there. The spring will build tension and will go back. And basically, you get a harmonic oscillator. It's oscillating. It's going do, 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 do. Okay. Listen, I'm not a physics professor. Please speak to your actually proper trained quantum mechanics. Actually, to be fair, this is just classical. Uh, today we surface a surface. Today we take the conductor's hypothesis and we conjecture ahead precisely. That's you can get a lot more. You can get away with a lot more by conjecturing. I think a lot of people get into problems because they're like, "This is the way it is." Did you speak with the Almighty recently? Perhaps they did. I don't know. Maybe they have some divine insight. It's last time I checked, I'm just a meaty bag of bones and stuff like that. So you might argue we are part of the divine, but that's a philosophical thing. Okay, so we got our spring over here. Here, let me actually open my eraser thing. All right, now we're gonna erase our springy thing. Why? Because we're gonna take this. We're actually going to delve into what the heck I mean by a Planck spring constant. Okay, so let's go to the class, go back to our window. I wonder if I can just actually do this. Planck spring constant. Don't know if that's listed in Wolfram as a thing. I don't think it is. Yeah, we'll just do spring constant. Okay. Physical quantity, because we want the dimensions of reality. Okay. Spring constant physical quality, yeah, because K's not used for anything else useful in physics. All right, so it's mass divided by time squared. Okay. Since it's got the little minus sign, that means that time is in the denominator. Okay. Oh, scalar is wait, scalar is not supposed to be a vector. Okay, so mass. So here's what we're gonna do. We're gonna do Planck mass divided by Planck time squared because that was one of the dimensions it told us. Okay. Okay, so the Planck mass divided by the Planck time to give us the Planck spring constant is 7.488 times 10 to the 78 kilograms per second. Wait a second. Wait a second. This number looks suspiciously familiar. 7.488 times 10 to the 78. Where have we seen that number before? Let's take out the Planck pressure. What was I think we can just go back. Wait a second. Wait a second. We just had our conjectured value for the sum total of mass of universe times c squared. So the total mass energy of mass. We use it because there's still more energy and stuff. We take the mass energy equivalent of the sum total of mass of universe. We get 7.488 times 10 to the 78 kilograms meters squared divided by wait a second. Those dimensions are slightly off. 7.488 times 10 to the 78. 7.488 times 10 to the 78. What's going on here? So let's take this whole expression. We're going to copy it. This is our Planck spring constant. We throw in our pretty protective brackets. Okay. We'll bracket these guys. Bracket divide. Do your thing. What do we get? Oh, we get 1 meter squared. Wait. There's a claim of the sum total of mass, its energy equivalent, divided by the Planck spring constant, that thing that helps restore balance. is 1 meter squared? That's interesting. Hey, Dave. We're just uh, we're just kind of slowly going through the conjecture. It's really large number hypothesis. So, the, oh, I should probably complete the square. Oh, you see what I did there? Waka waka waka. Wow, I'm so going to hell. So it's 1 meter squared. So the claimed mass sum total of the universe, realm of persistence, times the speed of light squared, divided by that Planck spring constant, gets us 1 meter squared. I think that's pretty neat. I'm very biased. It's suggestive, but it's all right. Professor Dirac, basically, back in the day, he noticed some similarities between certain like really large numbers and really small numbers, so like the radius of the electron, like the radius of the observable universe and stuff like that at the time. And he's kind of hypothesizing, conjecturing. He's like, oh, what if we have this? What if we have this? Maybe there's something there. I know. Dr. Unziker has been talking about this, and some other folks have talked about this, and it's like for me, it's like, all right. I just look at what like Thad basically taught me. It's like, oh, maybe we'll look at some interesting comparisons between these different things. So I'm like, all right. So Salvatore Pies do some of this stuff. I saw Rick use some of these factors. I'm like, all right, well, I'm not as smart as those people. What can I do? Let me go down a Wolfram hole and go down Codata, go down wiki holes and everything, and just like play around, play around, play around. Listen, I'm a gamer. I'm not going to claim to be a physicist. I'm a gamer. I like gaming. And one of the things you learn within gaming is to use creative use of game mechanics. So it's like, all right, you see all these relationships. It's like, all right, well, I can do some numerology. Let me look at it. I'm like, all right, well, this is cool. This is cool. Blah, blah, blah. Then things don't work. And then I get all frazzled. And then you drink more coffee because you need to have multiple, I don't know, existential issues. Or was it, I keep on forgetting the doctor's name. It was on with Sean Carroll. Yeah, you have an like 3 cups of coffee, an existential crisis a day, and then you can do physics or particle physics or something. But I just look at these things, and to be fair, we kind of got this. At first, I was like, "Oh, we need to do a hypersphere, and it's going to be basically the inverse of whatever it is in its dimensional units." So I'm like, "All right, well, you just write this as 1 meter over 1 meter squared over Planck length." Oh, look, we got our 1 meter squared. I can take off the yes. Here, we can write a one here to make me feel better about it. There. Hmm. I feel sometimes it's useful to. Oh yeah, 1 meter. There we go. We got our 1 meter squared, our 1 meter squared, our 1 meter squared. I think it's pretty. And again, I'm also very biased because I'm the one talking about this stuff. So, it's, is this the actual dimensions of our realm of persistence, our universe, so to speak? Maybe. Yeah, I ain't God or anything like that. I didn't. I'm not here to tell you the answer to the life, the universe, and everything. I'm just here, just conjecturing with the rest of you all, because the one beautiful thing about the internet is, well, you never know who's watching, for better or worse. I think that's one of the constants on the internet. So I don't know if the Planck force times the mass of universe times c squared could be equal to the radius of universe or whatever that means. I don't know. I just plug some numbers into Wolfram Alpha. It gives you an answer. It's like, all right. Is there anything to this answer? Well, if you divide it by the Planck density, you get, what is it? You do this. U divided by Planck density. So we're going to do D sub P. Okay, that's yours. Divided by Planck density equals Planck length times 1 meter squared. We take m sub u, claimed mass of universe. We multiply it by c squared. Divided by the spring constants. We'll just do s because I'm a crazy person. Spring Planck equals 1 meter squared. And you could also do this one. Claimed mass of universe, c squared over Planck density. No, excuse me, Planck pressure. So do B sub P equals 1 Planck length times 1 meter squared. Now, I understand that. I know I'm just saying words. I'm just saying words. I'm just relating them to the basic units that we've been using for a long time. Mostly because that's like, oh, this is probably how it is. So it's like, oh, you do some calculations. All right, well, that's kind of cool. We got some numbers. And to be fair, it was listed as a Planck temperature before, but I asked that about that because he had done that, and it's like, well, it should probably be the inverse of length. So I'm like, all right, let me do the inverse of length. And then when you do those calculations, these line up. Most of these things tend to be about 8 orders of magnitude, or about 100 million times greater than our current observables as far as we know it. It might help explain some things. I don't know. Um, but this too is something I think is maybe worth writing a short little paper on. And again, I didn't come up with any of this. This is basically just Professor Dirac. He's like, there seemed to be something interesting going on. Let me relate these things. I'm just a crazy person that got a really good tip, and it's like, hey, maybe there's something here. And then you just use Wolfram Alpha, and it basically just does it for you. So it's like, let me ask you a question. What happens if I did this here? What happens if I did this here? And again, it's like, is this right? Probably wrong. Most things are wrong. But by knowing that we're almost certainly wrong, perhaps we can use as some intuition, kind of do that whole red team thing. It's like, all right, well, is there something better? Let's poke some holes in it. Because at first you do a calculation, like, oh, that's a fantastical calculation. Do the Planck force thing. 10 to the 61 kilograms. How do I verify that? And, I don't know, let me do it some other ways. And you seem to be getting out basically just about the same number. And at least depending on how we have our error and everything set up. But I'm like, can we boil it down to simpler things? Well, at least according to Wolfram Alpha, this is about like 10 to the negative 8. We got at least 5 significant digits, 7 with error. This is about 1.6 times 10 to the minus 35. And we got that to about 5 significant digits, 7 with error. This is our defining one. We're relating this in relationship to that. Okay, let's square this whole little thingy because it's like 10 to the 69. All right. And then it's like, well, if we do that and then we solve for x over here, it's like, well, that mass of the universe seems to be suspiciously close within the error that we're using to compute it of this number here, that 8.33 times 10 to the 61 kilograms, which which if you multiply it by c squared and you divide it by the Planck spring constant, you got 1 meter squared. That's pretty neat. And again, it's like, what do I make of that? What do I make of that is apparently you use this 1 meter squared for calculating the claimed radius of universe, 1 meter squared. Okay. You divide by Planck length. You take that 1 meter, we're not squaring it. We're dividing by the Planck length again, and we're squaring the whole dang thing. Okay. Oh yeah, and then when you take this number here, mass of universe, you divide it by the Planck density, you get 1 Planck length times 1 meter squared. You take the mass, claimed mass of universe, multiplied by c squared, divided by the Planck pressure, which is apparently one of the vacuum catastrophes, or it's one of the aspects in which some people are like, wait a second, we're applying the Planck unit for pressure, and it's going to be all throughout space. It's going to go up to like infinity because it's so ginormous. And instead, it's like, I don't know, is it like 5 times 10 to the minus 10 joules per cubic meter or something like that. I've got another calculation, probably write a paper on. But essentially, mass of universe times its mass energy equivalent via c squared, or combining into its mass energy equivalent, divided by the Planck pressure, we get 1 Planck length times 1 meter squared. And if you take claimed mass of universe, that's still such a crazy thing to say, times c squared. So we take the mass energy equivalent of the sum total of mass of universe, and we divide it by the Planck spring constant, we get 1 meter squared. I know there's some math, but this is why I say it's like, again, if there was something to this, it's just some stuff doing some things. What is this? This is math stuff, because we get the lowercase m. We use that for math. We're doing a u there because I'm a crazy person, and I'm willing to conjecture that this would be mass of universe in its relation to the Planck mass is going to be equal to 1 meter divided by the Planck length, and we square the whole thing. And then things seem to balance out at 1 Planck length times a meter squared, 1 Planck length times a meter squared, 1 meter squared. I mean, wouldn't that just beat all? Believe Vanessa said, nature is simple. I can't confirm that. Oh, hey, Ila. I'm sorry. Leah? Ilya. I'm sorry. I'm terrible with names. I'm not sure if that's supposed to be an I or there's two L's there. But welcome. Thank you for joining, my friend. But no, we're just going off some conjecture thing. And here's the thing. We're going to claim there's about 100 million times more mass and basically space, whatever that is, within the universe than what we can observe. That's a ginormous number. However, as technology improves, I think we only need to go up how many orders of magnitude? We shouldn't have to go up 8 orders of magnitude to measure for curvature. Because right now, I think the measurements on curvature, so basically, was it, you map out stuff in the sky, you try to calculate how it's receding and everything. And basically, if you're mapping out a triangle and it adds up to like 180 degrees, it's essentially, okay, looks flat. More or less, that's what it looks like. You start seeing like under 180 degrees, then I believe it's hyperbolic. And then if it's greater than 180 degrees, I believe it's probably closed. Open, closed. I might be inverting those. Uh, Irregardless, because I'm back in Massachusetts, and that's a word that we say out here. It means regardless. But basically, we should be able to measure it. I don't know. Within 100 years, if you had enough precision and you were to go out, it's probably going to view something like a hypersphere. that's the generalized claim. But I mean, hey, if it's not right, it's at least pretty. Perhaps it is trying to tell us something. Um, I don't think anything like this is actually going to be ruled in or out. Maybe you know what? Probably a good chance they could rule it out within my lifetime. Did you rule it in? It's probably 100 years. I don't know. Maybe in 50 years, if we leap forward ahead, that'd be pretty cool. But I'm probably not going to be around then. But it's a cool thing to think about. And especially if you see, my big thing was I got those numbers. I'm like, all right, so 8.3 times 10 to the 61 kilogram. What the heck does that even mean? And it's like, that doesn't mean anything. However, when you come across things like the Planck density and Planck pressure, you're like, WTF, what's going on here? What is this trying to tell me? This seems like something that maybe is important, that maybe we should pay attention to. Uh, Basically, because I had no idea why those were numbers. Like the Planck density, I'm like, all right, just because you just do like the Planck length over. Let's go back over here. This guy. Window. Because if you just go to like the Planck density, it's okay. Planck density is this ginormous number. So you can just do, just Planck mass because it gives you those units. Now let's actually just go for it. All right, so Planck density, the Wolfram alpha here, it gives you the dimensions. Gives you, so it's dimensions of mass. And since this is a -3 in the exponent, goes in the denominator. So we could write that out as like mass divided by the uh, help. Here we go. Like length cubed. It's in the denominator. And then we got our number, that ginormous number. As we can see, it's approximately the Planck mass density. 10 to the 96 kilograms per meter cubed. You're like, where would that ever make sense? I don't know. Maybe you divided a sum total of mass that's about 100 million times larger than our observable universe. I don't know. It's, I mean, it's a fantastical thing to think about. Again, grandiose, grandiose claims are going to require grandiose evidence. Why? Because I mean, I could sit here, I can conjecture until I'm blue in the face. Doesn't mean it's right. Now that's the thing we should consider. Because again, I know Kurt Chen Mungo, shout out to Kurt from Theories of Everything. He's brought up, it's like, okay, very often we'll use different AI tools. We'll go around to different folks and we'll talk to them. We will conjecture. We will make very bold claims. And especially if you have folks that agree with you, and especially if an LLM agrees with you. It's not like anyone pretend to be agreeable at all. But if you have things that give you validation, I feel like many human beings tend to enjoy being validated. God knows I do. But as great as nice words and things that we want to hear are, sometimes there are things that you might need to hear. Why? Well, if you're wrong, if I'm wrong, it's well, I'd want to know about this. I'm not just gonna just be happy going around and just being like, oh, as long as people think I'm right, that's fine. I would do something like that. I mean, I'm probably conceited enough to do that, but that's a personal failing there. I'm sure we're all just good boys and girls. But oh, Upcycle's commenting. The hypercylinder gets perfectly surrounded by a hypercylinder, but volumes will have a 2-to-3 ratio. Oh, very fascinating. Units. Okay, now my mind's a jogging. I think that sounds about right because I think Owen is about 2/3. What is it? Unit circ, unit circle. Spherical uh, unit cylinder. There we go. All right, let's just go to cylinder. Do that. Isn't this what Wolfram Alpha is for? Duh. Do cylinder. Okay, so area or length is 1, height is 2. That kind of reminds me of something you might see in quantum mechanics or something. Get that H. Surface area, surface area, volume. Yeah, pi r squared times height. Okay. Gonna be divided by 3. So let's do pi. There's 1. Oh, it's got a 1/12 in there. Oh, that's neat. The generalized diameter. Hmm. I wonder. Do the unit? Cylinder surface, finite cylinder. Cylinder, divide by sphere. Ah! Finite cylinder surface. Oh, no. There we go. The volume. A squared that. All right. Let's. And we can do this. Uh, uh. All right. I'm pulling up my little thing. Gonna do this right here, right now. We're gonna just do it all unit 1. Don't think that's gonna be very as useful. By 1 squared. That's the height of 1. Okay, so it just gives us pi in that version. Okay, that's his volume. Or pi 1, 4 pi a cubed, cubing it by 3, and pi. It looks like it's 3/4. I kind of just done that wrong, but I think it's 3/4. Oh, the new largest prime, Laszlo. I saw something. I see some videos, and all of a sudden it's like, here's tree 3. It's like a little dot. Like, oh, here's Graham's number, and it's like, here's how it looks like one of those black hole comparison videos where it's like you don't even know like the magnitudes at that point. It just becomes so ridiculously like. See this? Listen, again, this is a crazy person on the internet. I'm just conjecturing the universe, so to speak. For our realm of persistence, it's about 100 million times larger than what we see. That's really all. I mean, that's a really large number, but it's not infinity. I can count to like 15. Like, okay, maybe I can't count to 10 to the 34. I can count more digits out of 10 to the 34 than I can to infinity. That, assuming limit is greater. Um, we want to be as open and accurate as we can, but yeah, that's all we really got for today. So just playing around with this new board. We'll probably move some different stuff and things around. We'll see what happens. So I can even see a little bit of a window there. Yeah, need to fix up a bunch of stuff and things. But other than that, hey, thank you all for joining me now and temporally in the future. And yeah, it's a heck of a new year. Peace up and take care, everybody.